Alright, what's up guys? In this video, I'm going to pick up with some vector calculus here. We're going to be talking about Green's theorem, and this time we're going to be talking about the flux form, or using the flux form of Green's theorem to evaluate this double integral. So we have this double integral here, 2xy plus 4y cubed dA, where r is a triangle with the vertices 0, 0, 1, 0, and 0, 1. So what I went ahead and did prior to the video, and I will typically do this during the video, is I will do the sketch before the video. And typically the reason why I do that is because sometimes, depending on what it is, it can take a bit of a minute to sketch something. I probably could have sketched this one during the video. This one wasn't hard. All I did here was just sketch the triangle and put the vertices on. But in most videos that I do, I will take care of the sketch prior hand because, again, it can take a little bit of time, and I don't want to waste your time by spending half the video just trying to get the sketch perfectly right. Also, if I make a mistake on the sketch, when I'm doing it prior to that, I can always go back and change it. I don't have to worry about changing it while I'm going live. So that's the reason why I take care of the sketch beforehand. So we have the sketch here, and again, it just has our vertices, and we just want to use the flux form of Green's theorem. Now remember, Green's theorem has two forms: the circulation form, we talked about that in the last video, and the flux form. Which form you use would depend on the question. Okay, so all right, so what about the flux form of Green's theorem? What is it? Well, it's just going to be our line integral f dot n ds, and I'll explain what everything means, is equal to line integral f dy minus g dx, and that's going to be equal to the double integral, and it's going to be the partial of f with respect to x plus the partial of g with respect to y dA. Now, let's talk a little bit about this formula here, or this form here of Green's theorem. So again, you guys know from prior videos that the n here is just the unit normal vector on our curve C. So let me just write that down. That's just the unit normal vector. And remember, for Green's theorem here, these two line integrals over here are going to give us our outward flux. So it's going to give us our outward flux here. And then if you go over here to our double integral, we have the partial of f with respect to x plus the partial of g with respect to y. Recall that that is just the two-dimensional divergence. That's all that is. So if someone writes the formula, some people will write it this way. Instead of writing it as partial of f with respect to x plus partial of g with respect to y dA, they might just write divf. Well, if they write divf, just understand that that's the same thing as this. It's just that this is the two-dimensional divergence. So they might not write it like that. They might write they might write div f. So just make sure you know the difference between that. So that's the flux form of Green's theorem. How is it different? Well, it's only different really in terms of, well, the circulation form and flux form is obviously it's different and is applied in different circumstances. But the only thing that would be different in terms of you actually looking at it, instead for the circulation form, it'll be a subtraction sign as opposed to a plus sign. But there's obviously more differences. But if you're just looking at it for what it is, that's the only major difference in the formula, is the sign there. So let's go ahead and use it here to take care of this problem. So we now need to get our ranges for x and y here. So we're given a triangle here that I did a sketch of. Put it right there, that way I can see it. So based on the sketch here, we can easily get our ranges for x and y. So we need our ranges. All right, so our ranges for x here are going to be from 0 to 1, just looking at our sketch. And our range for y is going to be from 0 to 1 minus x. And that's another reason why you need to sketch. It's because you need to get your ranges. Okay. And we know that the dA, that's just going to be dy dx. That's the order in which you're going to integrate this. So we can set up a double integral and take care of it. Okay. So since we're doing this dy dx, we have to make sure that the limits of integration and the integrals match up with the differentials. So since we're doing this dy dx, the ranges for x are going to be from 0 to 1, so that'll be the outer integral. The inner integral will be from 0 to 1 minus x, and then we'll just simply have 2 xy plus 4y cubed, and we're integrating this dy dx, basically. So now it's just a double integral that we're going to deal with. So for double integral, as I mentioned, in this particular case, we're going to integrate with respect to y, treating x as a constant, then we'll integrate with respect to x, and we work our way from the innermost integral to the outermost one. So this will be from 0 to 1 minus x, and we'll simply have 2xy plus 4y cubed, and integrate it with respect to y. So recall that if we use the sum rule for integrals, recall that this is just the integral from 0 to 1 minus x, 2xy, integrated with respect to y, plus the integral from 0 to 1 minus x, and it'll be 4y cubed, integrated with respect to y. Now, like I said, you could do most of this stuff without having to write down extra steps. I'm writing down extra steps for the purposes of the video, so just keep that in mind. So let's go ahead and see what we get when we compute the two here. So we got 2xy integrated with respect to y from 0 to 1 minus x. So not only is the 2 a constant, but the x is also a constant since we're integrating with respect to y. So we know that this would just be 2x y squared over 2 from 0 to 1 minus x. And that'll just give me x times 1 minus x squared, if I evaluate that. And then if I go over here from 0 to 1 minus x, we got 4y cubed dy. Well, that's just 4 times y to the 4th over 4 from 0 to 1 minus x. And that'll give us just 1 minus x raised to the 4th power. So now we go out to our outermost integral, and we're going to integrate respect to x now. So from 0 to 1, we'll have 1 minus x. We need an extra parentheses. 1 minus x squared plus 1 minus x to the 4th, and all of that is going to be integrated with respect to x. So again, this is just going to be the integral from 0 to 1. It's going to be 1 minus x squared. I'm sorry. It's supposed to be an x out here, sorry. X times 1 minus x squared, sorry. Dx. And then it's going to be plus the integral from 0 to 1. And it's going to have 1 minus x raised to the 4th power, all integrated with respect to x. So we want to break it up that way. Okay. All right, now let's just deal with it. So we'll deal with the first one here. So the integral from 0 to 1, we got x times 1 minus x. Not 1 minus 2, 1 minus x, sorry. X times 1 minus x, quantity squared, integrated with respect to x. So we'll deal with that one first. So the first thing that you probably want to go ahead and do is just expand it out and take it from there. So if we expand this 1 minus x squared, we expand that out, and then, well, we'll FOIL it because 1 minus x squared, that's just 1 minus x times 1 minus x, and then we'll distribute the x in on top of that. And then what that'll give us is the integral from 0 to 1, and it looks like we're going to get x minus 2x squared plus x to the 3rd, and that's going to be integrated with respect to x, because essentially what we would get is 1 minus 2x minus x squared, and if we multiply by x, if we distribute the x in and expand, basically expand, this is what we would get. Now we integrate it from 0 to 1. And so in that case, this would be the integral from 0 to 1 for for x with respect to x. And then we'll just get 1/2. Then we got the integral from 0 to 1 for 2x squared. Again, that's just going to be 2 times x cubed over 3 from 0 to 1. And looks like we'll get minus 2/3. And then this last one here from 0 to 1, we got x to the third, but that's x to the fourth over 4. From 0 to 1, that's 1/4. So this would be plus 1 over 4. And 1/2 minus 2/3 plus 1/4 is 1/12, I believe, but I will check just to make sure. And I highly recommend you do this. That way you don't get your arithmetic wrong. Yeah, 1/12. So I went ahead and checked it just to make sure. So we get 1/12 for that part. And then we just simply integrate the next part from 0 to 1, and we got 1 minus x to the fourth, integrated with respect to x. So what about that one? Well, that's just going to be 1/5. Okay, all you got to do is use the power rule for that. I don't think we need to go through that. Hopefully you know how to deal with that. If you don't know how to integrate that, do a u substitution. But you really don't need to. All you really need to do is use the power rule. If you know the power rule, then that's easy to do. But if you wanted to do it step by step, you could do it using a u substitution and see that it works out to give you 1/5. I won't go through that. I'm pretty sure you guys got that down packed. Well, maybe I will. I guess I'll go through it just for the purpose of the video. So let's just say we did a u substitution. We let u equal 1 minus x, and then we get du, which is negative dx. And then if we did that, well, we'd simply have the integral, and our limits are going to change. And we just have negative u to the fourth power integrated with respect to u. We need to change the limits. If we change the limits, we're going to have to change the sign of the integral and flip the limits of integration, because essentially what would happen is we would have 1 as our lower limit of integration and 0 as the upper. So we would have to flip it and change the sign of the integral. So this would become positive u to the fifth after we did that. So let me just do it like this so you can see it. And what would happen is this becomes u to the fifth over 5, evaluated from 0 to 1, which would give us 1/5. So hopefully you were able to see how I got 1/5. So hopefully you could compute that one in your head. Just use the power rule. Okay. So what that does is that takes care of everything that we need to do as it pertains to those two parts, and all we really have to do is just add those two parts together, and that'll give us our answer. So when we computed the first integral with respect to x, we ended up getting 1/12, and then when we computed the second piece, when we applied the sum and difference rule for integrals, we ended up getting 1/5. So it's going to be 1/12 plus 1/5. And 1/12 plus 1/5, it looks like that's going to give us 17/60, which will be the answer here. So the answer for this will be 17/60. So your final answer for this problem, when we use the flux form of Green's theorem to evaluate this double integral, which was 2xy plus 4y cubed dA. When you use the flux form of Green's theorem, we get 17/60 as our answer. And that's how you do it. Alright. So I hope that made sense. Again, relatively straightforward process. A little bit more extra work on my end because I like to go through things in my video in great detail and not leave anything out. But that is how you do it. So let me know if you got any questions. We'll see y'all next time.